Hi students, let's go to the paper 2 of JEE Advanced 2025. First question given is from either salt analysis or organic characterization of organic compounds. Okay, you know Lassane's test. So during sodium nitroprusside test of sulfide ion in an aqueous solution, one of the ligands coordinated to the metal ion is converted to. We know the conversion occurring is nitroprusside changes to thionitroprusside ion. This is nitroprusside, and if sulfide ion is present in the aqueous medium, then this goes into the NO ligand and the complex is converted to a purple colored one of this form. So NO plus ligand is attacked by S2 minus to form NOS minus. Okay. So our answer is option A. That is called thionitrito ligand. The complete hydrolysis of ICl, ClF3 and BrF5 respectively gives. This is from P block. We know group 17 interhalogen compounds, okay, and their hydrolysis reaction general form is given in the NCERT book. The larger halide ion, which is often the central one, the larger halide ion is converted to corresponding oxo acid or its anion, and the other one, the side ones, are changed to hydrogen halides. That is the way they undergo hydrolysis. Thing is that oxidation number is not changing for the halogens present in the compound. So if ICl is undergoing hydrolysis, you know central iodine is in +1 state and Cl is in -1 state. So I changes to IO minus, in which again iodine is having +1 oxidation state, and Cl minus changes to HCl. So same way ClF3, you know chlorine is in +3 state and that changes to ClO2 minus, in which chlorine is in +3 state, and if fluorines change to HF. And BrF5, the central Br is having +5 state, therefore it changes to BrO3 minus, in which it is having +5 state, and all the fluorines converted to fluoride ions, okay, HF. So these are the one of the products formed in the hydrolysis reaction. So our answer is option A. So not change in the oxidation state of halogens during the process. Monocyclic compounds P, Q, R and S are the major products formed in reaction sequences given below. We need to identify the one having highest number of unsaturated carbon atoms. Okay, so for that we need to identify the structure, exact structure of P, Q, R and S. Let's first do that. This is altogether HVZ reaction. So it is giving us alpha halocarboxylic acid at the end. In between we have an acyl halide formation also with an alpha halogen atom, and its hydrolysis gradually gives us this carboxyl unit, okay, that leads to regeneration of carboxyl unit during the HVZ reaction. You know the mechanism. Then this is aldol reaction, intermolecular, and it shows condensation reaction as well. So here we know this is the one with alpha hydrogen atoms and this is the one without any alpha hydrogen atoms. So from here to there reaction will occur in the presence of base. First the aldol forms. Let me quickly draw the aldol structure also. First the aldol forms like that, which goes to condensed products immediately by the general E1CB mechanism, leading to an alpha beta unsaturated aldehyde product like that. So that is the structure of Q. And in the next case we have a terminal alkyne and it is treated in presence of sodamide with an alkyl halide. You know, in presence of sodamide this is going to form an organometallic compound which is a nucleophile then. So C triple bond C minus Na plus is formed, which is due to acidity of the terminal hydrogen in the alkyne, and later it acts as a nucleophile for SN2 reaction, because this is an allyl halide which is highly promoting SN2 reaction on it. So that will firstly gives us, so the first product will be a higher hydrocarbon, 1, 2, 3, yes, that is allyl part, and which is then treated with H2O in presence of acid and Hg2 plus, which is hydration of alkyne center. So hydration of alkyne center will give us a ketonic product at the end with an intermediacy of the enol form. You know the mechanism of hydration of alkynes. It's altogether a Markovnikov addition, and here there is no difference in the nature of the either carbon atoms. So we can say it goes through the more stable carbocation case. The more stable carbocation possible for this particular alkyne will be a cation at the benzylic site, which can be then resonance stabilized. So cation is generated at the benzylic center with the addition of H plus on the other carbon, and here then the H2O attacks to form the enol, and that enol tautomerizes to that keto form. Okay, so in side chain we have 1, 2, 3, 4, 5 carbon atoms. So 1, 2, 3, 4, 5. So that is the expected structure of the final compound R. Now in the next case, first there is a reductive ozonolysis happening. So reductive ozonolysis happens in the alkene, and we will get a dicarbonyl compound like that, which has an aldehydic unit and a ketonic unit at two sides, and this is then treated with two equivalents of methyl magnesium halide. You know, one equivalent goes to the aldehyde and the other equivalent goes to the ketone. So followed by hydrolysis. Okay, let's first draw the structure obtained with the reaction of methyl magnesium halide, which is before hydrolysis. Okay, so that is a structure. We have entered two methyl groups into the overall structure, and this is now an alkoxide, and later we are treating with acid and heating also. Okay, when we treat it with acid, firstly an intermediate forms which has this outlook, and here, yes, it looks like that. And since we have applied heating condition also, we can expect dehydration of the alcohols, because aqueous medium is not shown. Okay, aqueous medium is not shown, so let's assume it is concentrated H2SO4. This is like concentrated H2SO4, and heating, which favors the elimination reaction through E1 mechanism, which is very familiar for us from alcohols or hydrocarbons in preparation of alkene section. Okay, so this is basically leading to alkene formation via E1 mechanism, and the expected products will be this one. For this alcohol, this is a tertiary alcohol, so this is the preferentially removed hydrogen plus, which leads to the more stable resonance stabilized alkene. And here we don't have any other option but to obtain a styrene-like structure. So that is the dehydrated form of this particular secondary alcohol, which is again benzylic alcohol also. Okay, so this is the structure of S. Then let me redraw it. Okay, so that is the structure of S. Now if we count the number of unsaturated carbon atoms in all these, in the first case 6 plus 1, 7 unsaturated carbons are present. 6, 7, 8, 9 unsaturated carbons are present. Here 6, 7, 8, 9, and in the last case 6, 7, 8, 9, 10. So S is having the highest number of unsaturated carbon atoms. The correct reaction that would produce a dicarboxylic acid as the major product is, first reaction, let's see, we are applying sodium cyanide onto a compound which contains alcohol and halogen group. Okay, so this is a halohydrin. So halohydrin, halogen is the leaving group and this is a very good nucleophile. So SN2 reaction will occur on halogen center and firstly we will get a compound of this form where hydroxyl group still remains over there. Later we are applying dilute NaOH on it. We know nitrile undergoes hydrolysis to form carboxyl unit. Let's assume cation is Na plus. In that case, this is the structure of product obtained, and later on acidification of this compound will get COOH, OH. So that is the structure of final product, which is monocarboxylic acid. Now, with bromine water, glucose gives gluconic acid, which has a single carboxyl unit in it. Next, a secondary haloalkane is given, alcoholic KOH is applied, elimination reaction will occur to form alkene. So that is an E2 elimination reaction. Now KMnO4 H2SO for heating, oxidative cleavage will occur. Firstly, an aldehyde forms which further oxidize to, because this is a strong oxidizing agent, which further oxidize to a carboxyl group. So that we know from alkenes reaction section, oxidative cleavage reaction it is, and it leads to adipic acid. Okay, and that is the answer then, because we want a reaction which gives dicarboxylic acid. So C is the answer. Let's go to the last reaction also. This is chromic acid. Primary alcohol is oxidized to carboxyl unit. So this is the normal expected product. And if we assume, since heating is not shown, we don't have to proceed further. Okay, this is the expected final product. If heating was there, or if it is done under very harsh conditions, we may expect further degradation also, but in that case we will not be getting a compound having 2 carboxyl unit in it, because if this part undergo oxidation, there a ketone unit will be generated and here a carboxyl unit will be generated. So one fragment will be having a carboxyl unit and the other fragment will be having a carboxyl unit and a keto unit only. So it is no way going to give us a compound having 2 carboxyl units. So undoubtedly our answer is option C. So this is a section in which one or more correct options would be present. So the correct statements about intermolecular forces is: the potential energy between 2 point charges approaches 0 more rapidly. 2 point charges, this is ion-ion interaction. Ion-ion interaction approaches 0 more rapidly than the potential energy between a point dipole and a point charge. Okay, so ion dipole interaction, let's assume it is ion dipole interaction, and ion-ion interaction energy, potential energy, is proportional to 1 by r, and ion dipole potential energy of interaction is proportional to 1 by r square. So it is clear that this statement is wrong. Ion dipole interaction is the one which approaches 0 more rapidly as r increases. R is the distance between the 2 interacting centers. Okay, so due to the 1 by r square dependence, this is the one which vanishes rapidly as the distance between them increases. So A is a wrong statement. The average potential energy of 2 rotating polar molecules, okay, 2 rotating polar molecules, that is dipole-dipole interaction between 2 rotating polar molecules has 1 by r cube dependence. 1 by r cube dependence, that is wrong. That is true for stationary polar molecules. For rotating polar molecules, this is 1 by r raised to 6 only. Okay, that is a dependence of distance. The dipole-induced dipole average interaction energy is independent of temperature. That is a generally correct statement. And non-polar molecules attract one another even though neither has a permanent dipole moment. That is true. That is the London dispersion forces. There could be a momentary generation of a dipole in one of the molecule due to electron displacements within the molecule. Okay, electrons are moving here and there. If we imagine it as a particle, it moves through the molecular orbital, which is spread over the molecule, over the entire molecule, and therefore at some instant there can be an instantaneous dipole generation in one nonpolar molecule, and due to that instantaneous dipole moment creation in one of the molecules, a neighboring molecule may get an induced dipole also. So this instantaneous dipole, induced dipole, leads to an attraction between them, which is called as dispersion forces. So that is how two nonpolar molecules are attracted with each other. So C and D are the correct statements about intermolecular forces, and hence answers here. The compounds with phosphorus hydrogen bonds. All are oxyacids of phosphorus. First is phosphoric acid. Phosphoric acid has that particular structure in which no pH bonds are present, and H3PO3, phosphorus acid, has this structure in which one pH bond is present. Pyrophosphoric acid has that structure in which no pH bonds are present, and phosphenic acid has two phosphorus hydrogen bonds. So these are the two correct options which have reducing property also due to this structural aspect. This is more reducing than that. For the reaction sequence given below, the correct statements is or are. Firstly, benzoic acid preparation occurs. This is a benzene holding alkyl groups which has at least one hydrogen at the benzylic site. So these two alkyl fragments get oxidized to carboxyl unit. So firstly, phthalic acid is obtained. COOH, COOH. Later, with ammonia heat, firstly, ammonium salt is formed. If we simply add ammonia to carboxyl unit, salt will form. And if we heat it to some extent, two H2Os are removed from these two units to form amide, which is phthalamide. So this is the structure obtained after two H2O loss. Now, so that is the structure of X. Now, strong heating of phthalamide will lead to phthalimide. Imide formation will occur. With ethanolic AOH, it forms phthalimide salt. Potassium salt of phthalimide is formed, which then treated with RBR. So we can expect an SN2 reaction between the phthalimide ion, which is nucleophile, and the electrophile RBR, and N-alkyl phthalimide is formed. So this is the popular Gabriel phthalimide synthesis. N-alkyl phthalimide is formed. We know that this R cannot be aryl group. Okay, on aryl halides, this particular transformation will not occur. So this is the structure of Y. Now, this on treatment with NaOH, which is aqueous NaOH, undergo hydrolysis of the imide to form two compounds. One is sodium salt of phthalic acid, and the other is RNH2, primary amine. So it's a preparation of primary amine, primary aliphatic amines only. Okay, so let's now identify the correct statements given out of the 4. Both X and Y are oxygen containing compounds. X is having oxygen, Y is also having same number of oxygen atoms. So this is a true statement. Y on heating with chloroform KOH forms isocyanide. Y is an imide. So this is a general test for amines, primary amines. So this is not a correct statement. Okay, Y has to be a primary amine, then it is giving us isocyanide test. Z reacts with Hinsberg's reagent. Z reacts with Hinsberg's reagent is correct because that is a primary amine. Even if it is secondary amine, it will react with Hinsberg reagent, but Z cannot be secondary amine, that we know. So the thing is that both primary and secondary aliphatic or aromatic amines can react with Hinsberg's reagent. Now, Z is an aromatic primary amine. Z cannot be. Z is a product of Gabriel thialamide synthesis, so it cannot at all be aromatic primary amine. It is a primary amine, but it cannot be aromatic primary amine. Okay, so only A and C are the true statements given. For the reaction sequence given below, correct statements are, firstly we are given with an ester, which is a cyclic ester. Cyclic ester is reduced with lithium aluminum hydride. We know alcohol is formed. Alcohol is the product because it's a strong reducing agent. If it were diballage, then we will be getting a aldehydic unit at this side and on the other side a hydroxyl group. Okay, but ester with LiLH4 will be completely reduced to alcohol. Since this is cyclic ester, we will be getting a diol compound. Okay, diol is produced. So an alcohol unit on the carbonyl center and an alcohol unit at the alkoxy center also, which is basically leaving group. That is, this is not involved in reduction. This is the actual center which is undergoing reduction. Okay, and that reduced it to alcohol, and this leave the molecule as an alcohol. Okay, basically we are ending up at a diol compound because this was a cyclic ester. So then this is treated with CrO3H2SO4. Oxidation will occur. Primary alcohol will undergo complete oxidation to carboxyl group. Primary alcohol will undergo complete oxidation to. Nextly, P is treated with CrO3H2SO4 reagent. We know primary alcohol will undergo complete oxidation to carboxyl unit. So 2 carboxyl group containing product is obtained. That is the structure of Q. Later, NaOH-CaO heat, that is soda lime decarboxylation, both the carboxyl group will be removed and is replaced with hydrogen atom. So these 2 carbon change to methyl groups. Okay, so that is the structure of R. Now P is treated with H2SO for 443 Kelvin. This is a dehydration reaction. Yes, so let's assume both the alcohols are undergoing dehydration. So this is one of the possible intermediate structure during the dehydration process, and you know dehydration, since it is carried out in presence of H+, there are all the chances for isomerization of the alkene formed initially. Okay, and also it is going through carbocation intermediates, right? There are multiple possibilities in this particular reaction. First of all, this was a primary alcohol. So there are all chances for rearrangements of the carbocation if any form during the reaction if we assume even mechanism, or else if the alkene forms also by direct elimination, then also there are chances that the alkene may get protonated to form a new carbocation which then undergoes rearrangements to form more and more stable alkenes at the end. So here let's assume this alkene is getting protonated again and a secondary carbocation forms here, followed by a hydrate shift to that center, followed by one more hydrate shift to that center to form finally a benzylic alkene unit, okay, here. And the expected final product for this reaction is then 1, 2, 3, 4, 1, 2, 3, 4, okay. So that is the expected final structure of the product. Okay, because this is highly stable alkene now. All the double bonds, all the pi bonds are in conjugation with each other. So this is an extended conjugated alkene which is highly stable. So this is the expected structure of S. Okay, although this is an intermediate possible structure, this is the final expected structure which is a more stable alkene form possible in the conversion of P to S. Okay, so we identified structure of P, Q, R and S. Now let's identify the correct statements about them. P is optically active is a wrong statement because it is not having any asymmetric carbons. This is not asymmetric, this is also not asymmetric because these two are identical groups. Okay, so it is not having any asymmetric carbon atoms, so it's basically optically inactive only. S gives Bayer's test. S is having alkene units, so it can give Bayer's test. Q gives effervescence with aqueous NaHCO3. Q has carboxyl units, therefore it can evolve carbon dioxide with sodium hydrogen carbonate. R is an alkyne? No, R is an alkane. So only B and C are true statements. So next we are moving to numerical section where we have to enter our answer correct up to 2 decimal places. Okay, such 8 questions are present in this paper 2. The density of metal which forms a cubic closed packed lattice with an axial distance or edge length equal to 400 picometers. So this is a direct question from solid state, our extra topic. So density of a solid is mass of 1 unit cell divided by volume of 1 unit cell, which has the final form Zm divided by Na A cube. So this is an FCC lattice. Therefore Z value is 4. Effectively 4 atoms are present in 1 unit cell and molar mass in grams per mole is 105.6 and Avogadro number per mole A is given as 400 picometer. So let's substitute the values. 4 into 105.6 grams per mole divided by 6 into 10 raised to 23 per mole times A cube, which is 400 picometer. A value is 400 picometer and in centimeter because we need density in gram per centimeter cube. So if we convert 400 picometer into centimeters, that is 4 into 10 raised to 8, 4 into 10 raised to minus 8 centimeter, its whole cube. So this expression is directly giving us an answer in gram per centimeter cube, which is 11. So our exact answer is 11, although IITK has given a range like 10.85 to 11.1. So whoever could write the answer in this particular range has got full marks for this question in the actual examination. The solubility of barium iodate in an aqueous solution prepared by mixing 200 ml of 0.01 molar barium nitrate with 100 ml of 0.1 molar sodium iodate is. Let's identify the formula first. Barium iodate means BaIO3 twice. Iodate is IO3 minus. This is barium nitrate and sodium iodate. Okay. Now, so we have basically mixed barium nitrate with sodium iodate. How many moles of each? This is 2 millimoles of barium nitrate with 10 millimoles of sodium iodate. So, barium nitrate is the limiting reagent here. We know the reaction is simple precipitation reaction. Let's write the balanced equation for that reaction. Barium nitrate reacts with sodium iodate in 1:2 form to form BaIO3 twice, which is a precipitate, which is confirmed from the Ksp value, plus 2 sodium nitrate, which is soluble. So, soluble ones we write with the aqueous in bracket. Okay. So, there is a reaction happening. So, we have taken 2 millimole of this one with 10 millimole of NaIO3. Initially, we didn't have any of those products present in the medium, and a reaction worked. It went to 100%. So, all the limiting reagent got consumed. Now, we don't have any barium nitrate in the medium, and for 2 millimole of barium nitrate, there will be 4 millimoles of sodium iodate reacted with it. Okay, so after that 6 millimoles of sodium iodate will be remaining in the mixture, and from 2 millimole of barium nitrate, 2 millimole of barium iodate has formed according to stoichiometry, and 4 millimole of sodium nitrate also has formed. So, this is the final solution. Okay, so this is the final solution, and you know this is a precipitate, so it's not part of a solution. So, the actual final solution is containing these things only. So, that is a composition of the final solution, and this is staying away from the solution as a precipitate. And what is the volume of the solution then? Volume of the solution is 200 plus 100 if you assume volume of mixing is 0. So, 300 milliliter solution. So, the solution obtained on doing so. Okay, solution obtained on doing so is a 300 ml solution containing 6 millimoles of sodium iodate and 4 millimoles of sodium nitrate. And we need to find the solubility of barium iodate in this particular solution. Okay, solubility of barium iodate in this particular solution. So, solution is already carrying a common ion, which is iodate here. Okay, iodate obtained from sodium iodate. Into that we are trying to dissolve barium iodate solid. Let's find out the solubility of barium iodate in a solution containing this many sodium iodate and that many sodium nitrate. Okay, so let's go to the solubility equilibrium for BaIO3 twice solid. Okay, let's imagine we are dissolving barium iodate into an aqueous solution that already carries some iodate ions. So, initially we were having no barium ions in the medium, and we were having, what is the concentration of sodium iodate in the final solution? 6 millimole divided by 300 milliliter. Okay, so this is the molarity, 6 by 300. So, initially we had 0.02 molar of iodate ion in the taken solution. So, that is time t equal to 0. Now, as the process reaches equilibrium, okay, we have dissolved, or the added barium iodate start dissociating. So, some S dash amount of S dash concentration of barium ions have been generated in the solution now, and 0.02 plus 2 S dash of iodate ion is also present in the new equilibrium mixture. Okay, and this S dash is the solubility of barium iodate in a solution containing that much amount of sodium iodate. Okay, so we need to find, or we need to solve for S dash. And we know from common ion effect that this sum is very close to 0.02 molar because the Ksp of barium iodate is sufficiently low. So this solubility of barium iodate is going to be far lower than the normal solubility of barium iodate in pure water at this temperature. Okay, so this is the case in the saturated solution of barium iodate prepared with the initial solution, 300 ml solution. Okay, so we know law of chemical equilibrium is valid here, and law of chemical equilibrium says equilibrium concentration of barium ion times equilibrium concentration of iodate ion square. Is equal to Ksp of barium iodate, which is 1.58 times 10 raised to minus 9. So, very directly, molar solubility of barium iodate in this particular solution is 1.58 divided by 4 into 10 raised to minus 4. So, this is giving us some value in mole per liter units. So, the exact answer is 0.395 into 10 raised to minus 5 molar. And the question demands us to write it in the form of x into 10 raised to minus 6 mole per liter. Mole per decimeter cube is mole per liter only. So, this is 3.95 into 10 raised to minus 6 mole per liter. So, the value of x is exactly 3.95 and IITK has given a range 3.85 to 4.15 for this answer. So, whoever could report the answer within this range will be getting full marks in JEE Advanced 2025 paper 2. Okay. So, that was from ionic equilibrium. Next question brings us to surface chemistry topic, where Freundlich isotherm is described. Adsorption of phenol from its aqueous solution onto fly ash obeys Freundlich isotherm. At a given temperature from 10 mg per gram and 16 mg per gram aqueous phenol solutions, the adsorbed phenol concentrations are obtained as 4 and 10 mg per gram respectively. At this temperature, we need to find the adsorbed phenol concentration from a phenol solution having this concentration. Okay, right. So let's recall the Freundlich isotherm mathematical form. X by m equal to k p raised to 1 by n in the case of gases, or for aqueous or solutions. Okay, liquid solutions. This is also an accepted form of Freundlich isotherm. X by m equal to k c raised to 1 by n, where c is the concentration of the adsorbent. So, next question is related to Freundlich isotherm, which is described in surface chemistry topic. Okay. So, this is talking about adsorption of phenol. Phenol is the adsorbate in the aqueous solution onto fly ash, which is the adsorbent. So, adsorption of phenol on fly ash is the background, and at a given temperature from 10 mg per gram and 16 mg per gram phenol solutions. So, these are the concentrations of phenol. The concentration of adsorbed phenol are measured to be 4 and 10 respectively in the same units. Okay, so this is the adsorbed phenol concentration. This is the total phenol concentration in the solution. This is the adsorbed phenol concentrations at the end. At this temperature, concentration of adsorbed phenol, we need to calculate we need to estimate the concentration of adsorbed phenol from a different phenol concentration solution. Okay, So if you are given with 20 milligram per gram phenol solution, what would be the expected adsorbed phenol concentration? That we need to check. So Freundlich isotherm, let's recall the mathematical form X by M, which is basically the concentration of adsorbed phenol. So that is equal to K into C raised to 1 by N. General form is K into P raised to 1 by N, and for solutions, for liquid solutions, we can take K into molarity raised to 1 by N also, or concentration, basically concentration raised to 1 by N also. Okay. So remember, X by M and C, these are given in the same units. Okay. X by M, these are X by M's, and these are C's. Both are given in the same units. Right. Now let's try to solve it. So here the value of K and N are not given. So first of all, we need to find out the value of K and N from the given two datas. So for that, let's convert to logarithmic form also. Log X by M is equal to log K plus 1 by N log C. So let's tabulate the given data first. X by M, C. Or let's first mention C and then X by M in the sequence of the experiment. In the first experiment, when C was 10 milligram per gram, X by M was 4 milligram per gram. In second experiment, when C was 16 milligram per gram, X was 10 milligram per gram. And in third experiment, if you take C as 20 milligram per gram, what would be the value of X by M? That is a question. Okay. So for the first entry, let's make the equation log 10 is log X by M, which is 4. Log 4 is equal to log K plus 1 by N log 10. For the second entry, log 10 is equal to log K plus 1 by N log 16. Okay, if we solve these two equations, we can get the value of N, right? Because log K is common here, and if we take a difference of these two, that time will cancel out. So let's call this is equation 2, that is equation 1. If we do equation 2 minus equation 1, we'll be getting log 10 minus log 4 is equal to, these will cancel out, 1 by N log 16 minus log 10. Okay. So this is 1 minus 0.6 is equal to 1 by N, that is 2 raised to 4. So 1.2 minus 1. So N will be 0.2 divided by 0.4, which is 1 by 2. So we obtained the value of N as 1 by 2. So having obtained the value of N, we have now multiple pathways possible for further solving. One of the methods is to calculate the log K using the obtained value of N by solving one of these equations. Okay, and in that case you will be getting the log K as minus 1.4. Okay, log K will be obtained as minus 1.4. If we go that way, we need to find more number of logarithmic or anti-logarithmic values for which enough data is not given. So let's plan a different method. In a different method, we are going back to the original form of Freundlich isotherm, the non-logarithmic form, and into that we are using this particular N value to set up new equations. So without finding the value of K and going to the anti-logarithmic cases, let's go in a different direction. Let's set up the equation in this form for the first two entries. So x by m is equal to Kc raised to 1 by n. So x by m is 4 here. 4 is equal to K C raised to 1 by n, which is 10 raised to 2. 1 by n is 2. And in second row, 10 is equal to K into 16 raised to 2. And in third row, x by m is equal to same K into 20 raised to 2. Okay, these are the equations obtained. Now, we can either use first and third equations to solve for x by m in the third case, or we can use second and third case in a ratio manner to solve for x by m in third case. In both these cases, we are getting different answers. That is the other peculiarity of this question. So if we use 1 and 3, that means if we divide 3 by equation 1, we will be getting x by m divided by 4 is equal to k and k cancel out, 20 square divided by 10 square. So in that case, x by m is obtained as 16, a perfect answer. So the advantage of this particular method is that, okay, having obtained the n value following the non-logarithmic cases, we no need to take any antilogs in this solving process. Okay, that is the advantage, because we are not given with any anti-logarithmic values. Okay, so if you know how to use if you know how to find out antilog values, you may follow that. At the end of the day, you will be getting full marks if you could solve it correctly, because they are giving wide ranges. But no need of doing that. You follow the values given and try to follow different methods. Okay, easier methods. This is an easy way to calculate x by m. And if you use second and third rows, okay, in that case, x by m divided by 10 is going to be 20 square divided by 16 square. From there, x by m is obtained as 15.625. Okay. So that is the two answers obtained from this particular data. So actually, IITK has given the final answer in the range 15.5 to 16.5. So the ones who followed this way will get full marks, the ones who followed this way will get full marks, and the one who followed the anti-logarithmic way also will get full marks, because that way you will be getting a value in between these two. Okay, yes, so you follow any method, you will be getting full marks for this question. Next, we are going to kinetics topic. Consider reaction A plus R giving products. The rate of this reaction is measured to be KAR. Okay, the rate law is experimentally obtained as K times A times R. This at the start of the reaction, the concentration of R is 10 times the concentration of A. The reaction can be considered to be pseudo first order reaction with the assumption that K into R is a constant K dash, which is expected because concentration of R is plenty. Okay, R is in large excess compared to the other reactant A. So we may at times we may assume that concentration of R is not varying much. Okay, and it turns out to be a pseudo first order reaction, because this is overall second order reaction, first order in A and first order in R. If we assume this is independent of concentration of R, this is going to be a first order reaction, which is then pseudo first order reaction. Due to this assumption, the relative error in the rate when the reaction is 40% complete is. Okay, so let's write the balanced equation for the reaction A plus R giving products. So initially, concentration of A. So concentration of A is given as A naught, and concentration of R initially is 10 times A naught. no products were formed. At a later time, as the reaction reached 40% completion, so at a point where 40% reaction has been completed. So 40% reaction has been completed means 40% of the limiting reagent has been consumed. So only 0.6 A0 is remaining now. Remaining 40%, for 0.4 A0 has been consumed. And 10 A0, from 10 A0, for 1 A, 1 R is getting consumed from stoichiometry. So for 0.4 A0, 0.4 R is getting consumed. So 10 A0 minus 0.4 A0 is the final concentration of R when the reaction is 40% complete, that is 9.6 A0. Okay, and some amount of product has been formed. Right. If this is one product, okay, if the coefficient is 1, we can say exactly that this is 0.4 A0. Okay, if this is one product, then this is 0.4 A0 strictly from stoichiometry. Okay, assuming all are in the same phase, all are in the solution phase or all are in the gas phase. Okay, so that is why the clarity of products is not here. So we are not bothering about product side. Okay, also to deal with the rate law, we don't have to have the information about product. Okay, because this is talking about the rate of reaction for different concentration of reactants. Okay, the rate law, its background. Okay, so at initial time, this is the concentration of A and that is the concentration of R. At the final time, this is the concentration of A and that is the concentration of R. So initial rate we know, final rate we know, because rate law gives instantaneous rate. So what we actually want is yes, the error in the rate at 40% stage. So at 40% state, if we assume it as a second order reaction, that is a real case, and if we approximate it to a pseudo first order reaction, we will be getting two different values for the rate. So in first case, rate is equal to K into concentration of A, which is 0.6 A0, times concentration of R, which is 9.6 A0. Okay, this is the rate of the reaction if we take the general case of second order reaction. Now, if we assume or if we view this reaction as a pseudo first order reaction, then the rate is going to be K into concentration of A, which is 0.6 A0. That is not the excess reagent. So its actual value, its real value we have to consider. And when we write concentration of R, we need to take the original value only, the initial value only, because we are assuming in pseudo first order case that its concentration is not varying. So during calculation, we will pick the initial value of R concentration. Okay. So that is the rate of the reaction at 40% completion. If we assume the reaction as pseudo first order reaction throughout its course. So we need to identify the error occurred in this assumption. This is the actual value. Okay, this is the actual value. This is the assumed or approximate value as per pseudo first order considerations. Okay. So let's call this as rate and this is R dash. So the required error is R dash minus R divided by R. into 100. So this is the relative error, that is a percentage error. So from these expressions it is clear that if we consider a pseudo first order reaction, the expected rate at 40% completion stage is higher than the actual rate of the reaction. So we are focusing on that error. So R dash is K into 0.6 A naught into 10 A naught minus R is K into 0.6 A naught into 9.6 A naught. So we can take K into 0.6 A naught as common and take the difference of rest of the portion. There is a numerator divided by R, which is again K into 0.6 A naught times the actual rate, the true value, that is 9.6 A naught. So this is the erroneous that is a real value. So this multiplied by 100 is the final answer. You can see that these portions will get cancelled out, all the A naught will get cancelled out, and we are remaining with 0.4 and 9.6 in the denominator. So on solving this expression exactly, we are getting 4.166%, and IITK has given the answer in the range 4 to 4.25. At 300 Kelvin, an ideal dilute solution of a macromolecule exerts osmotic pressure expressed in terms of height of the solution. Solution density is given, where H is equal to 2 centimeter. If concentration of dilute solution of the macromolecule is 2 gram per decimeter cube, molar mass of the solute, the molecule, is calculated to be. Okay. So we know for ideal dilute solution pi is equal to ICRT, where we take I value for the macromolecule as 1. So CRT, and pi is represented in terms of solution height. So H rho G is equal to CRT. So this is the working formula here. Value of H is given as 2 centimeter. So 2 into 10 raised to minus 2 meter. Let's make it in the SI units. Then rho is the density of solution 1 gram per centimeter cube. 1 gram per centimeter cube is the given density of the solution. So 1 gram per centimeter cube is 10 raised to minus 3 kg per centimeter cube, and that is 10 raised to minus 3 into 10 raised to 6 kilogram per meter cube. So in SI units, density of the solution is 10 cube kilogram per meter cube, and acceleration due to gravity is given as 10 meter per second square, which is in SI units. Okay, this is equal to this is equal to concentration of macromolecule in the solution. So concentration of macromolecule in the solution in gram per decimeter cube or gram per ml is gram per liter is given. Okay. So 2 into 10 raised to minus 3 into 10 raised to 3 kilogram per meter cube. So gram per decimeter cube is converted to kilogram per meter cube, the SI unit, and this divided by molar mass. Okay, let's see, molar mass is, molar mass is Y. Let's put it as Y. Okay, some Y, and this overall will be having mole per volume unit. So that is the C factor. Now this times R. R is already given in the SI unit. So 8.3 joule per Kelvin per mole. This is SI unit only. Times T. T is 300 Kelvin. Okay. So every value being in SI unit, it's very straightforward. we will be getting the value of Y, which is the only unknown here, in SI units itself, kilogram per mole. The exact calculated value is 24.9 kilograms per mole, which is 24900 grams per mole, and we want to express the molar mass in terms of x into 10 raised to 4 gram per mole. So this is 2.49 into 10 raised to 4 grams per mole. Okay, where this is the required answer. Okay, 2.49. So exact value of the required answer is 2.49, and the range given here was 2.4 to 2.55. An electrochemical cell is fueled by the combustion of butane at 1 bar and 298 Kelvin. Cell potential is x by f, f is Faraday, into 10 raised to 3 volts, where f is the Faraday constant, value of x is. Okay, we need to find cell potential. We are given with standard Gibbs energy of formation of every substances involved in the reaction. So this is about combustion of butane. So C4H10 reacting with oxygen. Butane is a gas. This is gas at 298 Kelvin, forming 4 CO2s and H2Os. So 13/2 O2 is the required amount. So it is a balanced equation for combustion of butane, and we need to get the delta G theta for this reaction. This is the redox reaction also. You know, electrochemical cell works with redox reactions, spontaneous redox reactions. So this is a spontaneous redox reaction, and where number of moles of electron transferred is, you know, this is the reducing agent, that is the oxidizing agent. Oxygen is the oxidizing agent. So oxygen from its 0 oxidation state is changing to -2 oxidation state in the products. Similarly, carbon is undergoing oxidation. Carbon is undergoing an increase in oxidation state. So to get the value of number of moles of electron transferred for 1 mole of butane, you can either follow oxidizing agent or reducing agent. So here it is more easy to go with oxidizing agent, because on this side oxygen is in 0 state, and on that side all the oxygens are in -2 state. So 13 oxygen atoms in 0 state going to 13 oxygen atoms in -2 state, so -26. So overall reduction in oxidation state of oxygen is 26. So N is 26 for 1 mole butane. So the number of moles of electron transferred is obtained. Now we need to get Gibbs energy change for this redox reaction, standard Gibbs energy change for this reaction. 4 times CO2. You know, Gibbs energy of formation of products minus Gibbs energy of formation of reactants is the Gibbs energy of any reaction. So standard Gibbs energy of formation of products have been given. So 4 into -394 plus 5 into -237. This is the total Gibbs energy of formation of products minus Gibbs energy of formation of reactants. 1 into -18 kilojoule per mole plus 13/2 into 0. You know, O2 is the reference state of the element, which is assigned the formation enthalpy or formation Gibbs energy as 0. Okay, so on solving this expression, we will get standard Gibbs energy for the reaction in kilojoules per mole unit. In kilojoules per mole units, and that is -2743 kilojoules per mole. Okay, so why we have calculated delta G, why we have calculated number of moles involved? This is because if we want to find E0 of the cell, it's called, let's say we are going to calculate the E0 of the cell, because we are given with standard Gibbs energies. Standard Gibbs energies are related with E0 of the cell. Okay, So in our mind, when reading this question, in our mind this equation will come, and that is why we are finding delta G theta and N value for this reaction, assuming 1 mole of butane. Assuming 1 mole of butane. Okay. So here simply E naught cell is minus Gibbs energy of the reaction divided by NF. Okay. So Gibbs energy of the reaction is minus 2743 kilojoule per mole. So minus 2743 into 10 raised to 3 joules per mole. So it's an SI unit now, divided by N, which is 26 for 1 mole of butane, times Faraday. Okay. So this will be giving us the answer in volt. If we are taking Faraday in coulomb per mole units, we will be getting answer in volts. So we need to express the answer in the form of some x divided by f into 10 raised to 3. So this 10 raised to 3 we can preserve in the numerator, and this f we can preserve in the denominator. So finally our answer is going to be 2743 divided by 26. So this is the value of x. So 2743 divided by 26 will be 105.5. So our answer is exactly 105.5. Answer is exactly 105.5, and they have given a range 105.4 to 105.6 for this question. Okay, so that was from electrochemistry. The sum of spin-only magnetic moment values of two manganese 3 plus complexes. So both are having manganese 3 plus in the center, and its electronic configuration as per CFT is T2G3 and EG1 because of weak field nature of bromide ligand, and because of the strong field nature of cyano ligand, T2G4 EG0 is the configuration for second complex. So here number of unpaired electrons is 4 and there it is 2. So spin-only magnetic moment will be root of 4 into 6, which is 2 root 6, which is 2 root 2 root 3 Bohr magneton there, and here root of 2 into 4, which is 2 root 2. And square root of 2 and 3 has not been given. If you take root 2 as 1.41 or 1.414, and if you take root 3 as 1.73, you can solve this expression, okay, and get some value in Bohr magneton units. So that way you may get 4.88 here and 2.82 there, and on adding those you will get 7.7 as the total value, and the IIT has given the answer in the range 7.5 to 7.8. That means even if you assume the general case that, okay, if there are 4 unpaired electrons, the Bohr magneton will be close to 4.9, and if there are 2 unpaired electrons, the answer will be close to 2.9, the general case. In this is the way we'll just memorize this data, right? If there are 1 unpaired electron, its value is very close to 2, okay, and if there are 3 unpaired electrons, its value is very close to 4. So that general case also will be included in this range. Okay, 4.9 plus 2.9 will be 7.8. So you take whatever values you want, up to 2 decimals or 3 decimals, 1.414, 1.732, everything will be included in this range. So you are safe. A linear octasaccharide of molar mass 1024 grams per mole on complete hydrolysis produces 3 monosaccharides, ribose, 2-deoxyribose and glucose. Okay, all molar masses have been given. The amount of 2-deoxyribose formed in the hydrolysis product is 58.26 weight percentage. The number of ribose units in the molecule is, okay, so initially we had taken octasaccharide, let's say O, with mass 1024 grams, and we hydrolyzed it. You know, in hydrolysis we are adding basically 7 H2O molecules. Because this is an octasaccharide, there will be 7 glycosidic linkages, and those glycosidic linkages are getting 7 H2O molecules. And the hydrolysis products is already containing, you know, deoxyribose, ribose and glucose, and the total mass of the hydrolysis products, let's call it H. The total mass of hydrolysis products will be 1024 plus 7 into 18, because overall it's just an addition of water. Okay, water mediated lysis of the glycosidic linkages. So with respect to mass of the substances involved, this is an addition of water only. Okay, so total mass of the hydrolysis products, if we start from 1024 gram of octasaccharide, is 1024 plus 7 into 18. So total mass of the hydrolysis products will be 1150 grams then. And they are saying that in this 1150 grams, it's 58.26 percentage is the mass of 2-deoxyribose. So 1150 into 58.26 divided by 100, that is 670 grams. So 670 gram is the weight of 2-deoxyribose. And we know the molar mass of 2-deoxyribose is 134. So 670 grams 2-deoxyribose means 5 moles of 2-deoxyribose. So from that information we get the idea that 1 mole of octasaccharide contains 5 mole of 2-deoxyribose. That is, 1 octasaccharide contains 5 deoxyribose units. Remaining 3 will be ribose plus glucose. So it could be like 1 glucose and 2 ribose, or it could be like 1 ribose and 2 glucose. These are the only two possibilities. Okay, these are the only 2 possibilities. So we need to find the number of ribose. So answer could be either 1 or 2, because total has to be 3 then. 5 is already 2-deoxyribose. Okay. Anyway, let's proceed in a mathematical way. The number of ribose units present in 1 molecule of octasaccharide. If we know that if we remove 670 grams from this hydrolysis products, the remaining mass, that is 480 grams, will be the sum of ribose plus glucose units. Since we want to find the number of ribose units, let's put the value of ribose, number of ribose as n, and number of glucose as 3 minus n, because the total is 3 molecule. There are 5 molecule. Okay. We are given with the ribose molar mass as 150. So 150 times n plus 180 times 3 minus n has to be 480. So very easily you find that n is 2. So number of ribose units is 2 in this octasaccharide. So its answer will be a perfect 2 only, right? So that completes the question paper. Thank you.